in Minnesota, it pays to pay close attention to our roads. We depend on good roads to carry most of our goods and services, and we spend a large share of each tax dollar to build and maintain those roads. Hello, I'm television meteorologist Mike Fairborn. Weather is certainly one important factor that affects the condition of Minnesota's roads. Sun, rain, snow, freezing, thawing, all are at work breaking down our road surfaces. But there's a second key factor that causes our road surfaces to deteriorate, and that's the weight of heavily loaded vehicles. Everyone knows that old joke that we all talk about the weather, but nobody does anything about it. I'll have to admit that's pretty much true for me. All I can do is predict the weather so that we're prepared for what's coming. But there are some people who do something about the weather, at least about the effect of weather on roads. They also do something about the effects of heavy loads. I'm talking about Minnesota's county and municipal engineers. I'd like to show you some of the things I've learned from engineers responsible for pavement construction and repair. I've learned that good sound pavement design methods can help to resist those two forces of destruction, weather and heavy loads. I've also learned that we can increase the lifespan of our roads and save money at the same time. To understand how that's possible, it's important to know some basics of pavement design. Now here's a cross-sectional scale model of a typical blacktop or asphalt surface pavement. By the way, I'm using asphalt pavement as an example here rather than concrete because about 90% of Minnesota's paved local roads are asphalt surfaced. Most pavement is composed of 3 layers. Here's the asphalt layer that we drive on. Its main purpose is to resist wear from vehicles. It also provides some of the strength that supports vehicles and keeps the other layers in place. Under the asphalt surface, there's a layer of compacted gravel called the pavement base. The pavement base is put down before the asphalt is laid. It supports the asphalt uniformly and spreads out the load of each passing vehicle. That's important to avoid damage to the asphalt. Under the base, there's the soil that was on site or was brought in from nearby. Engineers call it the subgrade. Before placing the base and asphalt, up to 5 feet of subgrade soil may be dug up, mixed to make it more uniform, laid down again, and compacted. That also helps to spread loads out over a wider area so that the pavement can handle heavier trucks. With a lot of the complex engineering details left out, that's how our roads are constructed. Now, let's see what happens when a heavy vehicle puts a load on the pavement structure. I'll provide the load. You can see that the load affects all 3 layers of the road structure. The important thing to know about the asphalt layer is that the load has opposite effects on its top and bottom surfaces. The top surface gets compressed at the same time the bottom surface gets stretched. This stretching is where a lot of road damage begins. If the bottom surface stretches enough, cracks will form. You can see them beginning here on our model. Each time a heavy load passes, the cracks grow. We notice the cracks when they reach the top surface and the pavement begins to break apart. This breakdown can occur 2 ways, slowly over time or all at once from a single very heavy load. We can see the same thing happen in almost any solid object. This sheet of plastic makes a good illustration. If I bend it over and over, but just a little bit each time, it finally fatigues enough that it breaks. But I can also break a sheet all at once if I bend it far enough. Engineers refer to the result of this bending as fatigue. Enough fatigue, whether it happens over time or all at once, and you get the same results, a broken sheet of plastic or a broken road surface that needs repair or replacement. We'll get back to this idea of fatigue again in just a few minutes, but first, let's see how loading affects the other 2 layers of the road structure, the base and the subgrade. These layers react differently than the asphalt because they're not bound together. They're made of compacted rock and granules of sand. So bending and fatigue are not factors here. Instead, what we're looking for in these layers is support, to spread out the load. That will keep cracking of the asphalt to a minimum. With the right combination of materials, the load of each passing vehicle is absorbed and the whole structure bounces back to its original shape, ready for the next load. I've got a videotape queued up over here that'll give you a pretty dramatic example of what I'm talking about. This video was shot by the U.S. Forest Service during some testing they did in Nevada. The pavement you see here was laid just to see how the breakdown of pavement progresses. Watch closely as the truck passes and you can see how the pavement layer actually moves as the truck goes by. And you can see that the pavement is starting to break up. This is edited down quite a bit. It took 81 passes by the truck for the pavement to reach this condition. Obviously, that much damage is very costly, so we need to avoid it, and there are several tried and true methods for doing just that. One of the most effective methods is to use multiple axles to carry a heavy load. This truck has a tandem axle, 2 axles set close together. The idea of a tandem axle is again to spread out the load to avoid fatiguing the asphalt. Now we've got lines here to help us compare the road's reactions to loads carried on single and tandem axles. First, the single axle. Let's see here, with the load I'm putting on the road, the bottom of the pavement layer is right about at the 1.5 inch mark. Now I'll try the tandem axle. I'm trying my best here to push down with just the same amount of pressure so the loading factor is the same. And as you can see, the pavement is bending down to only about the 3/4 inch mark under each of the axles. Pavement engineers use the term deflection to refer to this bending action of the pavement. Now that's about what we would expect. Double the number of axles and you reduce the deflection by half. In fact, though, there's more benefit from using tandem axles than you might guess. It turns out that the actual amount of damage done to the pavement by a given tandem axle load is less than half as much as the damage done by that same load carried on a single axle. The reason for that goes back to the idea of fatigue that I explained before. Because the asphalt layer is not deflecting very far under the tandem axles, there's less fatigue. So again, the truck can bend the pavement this far many, many times before it would begin to show damage. Also notice that even though 2 axles are going over the road, there's really just 1 deflection. See here between the axles? The pavement doesn't come back up before the second axle rolls over it. Fewer bends means even less fatigue. So tandem axles are really a pretty good idea. As a matter of fact, adding a 3rd axle to a truck will reduce road damage even more. This is done for newer model tractor trailers that carry heavy loads. Actually, trucks can be fitted with almost any number of axles to allow them to carry extremely heavy loads with very little damage to the pavement. It's a simple idea, but it's very important. Spread out the load. Just one statistic to support this point. A single pass over a road by a truck with 9 tons per axle will do as much damage to the road as 10 passes by a truck with 5 tons per axle. Now, while I'm setting up for the next demonstration, I'll just let you think about that. By the way, pavement engineers have formulas all worked out to determine how many axles should be required for any given load. Well, now I'd like to bring my favorite subject, the weather, back into the picture, and that's important because weather and vehicle loading are closely related when it comes to keeping our roads in good condition. Here in Minnesota and in other northern states, there's a special problem to deal with in managing the roads. That's our spring thaw. Even though we're all happy to see it each year, spring is actually the time when our roads are at their weakest and are most vulnerable to damage. Again, we can see why that is by working with the pavement model. But this time we've made some changes to simulate the spring thaw situation. Up here in the North Country, it's common to have a hard freeze down to 5, 6 feet below the surface, way down. All the moisture in the ground condenses into water and freezes, so the base and the subgrade become solid. Well, that turns out to be a positive for our roads. They have their greatest strength in the dead of winter. There's hardly any deflection in the pavement, even from very heavy loads. But then, spring has sprung, and since the warming comes from above, the base and the subgrade materials thaw out from the top down, and that's where we start having problems. When the air temperature reaches about 35 to 40 degrees for several days in a row, we get the situation represented by this model. The asphalt layer is still fairly stiff and brittle, but the base layer underneath has thawed out, so the gravel here is mixed with water in pretty much of a slurry condition. Meanwhile, the subgrade underneath is still frozen. The base is pretty much caught between a rock and a hard place. Now, here comes our truck, and I think you can see that trouble is on its way. With very little support from the mushy base and a frozen unyielding subgrade underneath that, the brittle asphalt layer now takes pretty much the entire force. And if I put enough load on it, it'll break even from a single heavy load. This is exactly what happens on real roads in the spring, and we're all familiar with the result. Pothole season. This is a big problem. St. Paul's Department of Public Works estimates that in 1990 it spent about $5,500 on repairs for each one of its 322 miles of city streets. Now, we can't make the Minnesota weather go away, so what can be done about this problem? Well, the answer is something that we should already be doing, and that is setting and enforcing reasonable spring load restrictions. Here again, our county and city engineers can help. They have reliable methods for determining pavement strength during the spring thaw, and they can calculate reasonable load limits once they know the pavement strength. There's also several ways to determine when the load restrictions need to be imposed and when they can be removed. Here's one of the most common methods used in Minnesota. This is a protective sheath, and the part that does the work is inside. It's called a frost tube. The ones used in the field are about 8 feet long. This short one is just for demonstrations, and we've had it buried halfway in the ice and snow for a while, and you can see that it's doing its job. The chemical dye inside, called fluorescein, changes color depending on whether it's above or below the freezing point of water. All the engineer has to do is keep several of these tubes in the ground in selected places near the pavement and then check on them every so often. More and more now, frost tubes are being replaced with much more precise sensors, but this is kind of interesting to look at, and it gives you the idea. Well, the engineers can help us set the load limits, but they really can't get the job done alone. We need a team approach if we're going to protect our investment in pavement. State, county, and city officials, road users, law enforcement officers, and judges all have to work together with the engineers on this issue. Funds have to be set aside for testing, informing users, and posting the limits. And we need to enforce those limits. I'm trying to do my part here by providing a little education on the fundamentals of good road design and maintenance, and almost everyone needs that. The best news is that the cost of these preventive measures is just about guaranteed to be less than the cost of road repair or reconstruction after pavement becomes damaged. Well, now I want to hazard a guess as to what you're thinking. As I was demonstrating the problem that comes up in the spring, you may have been wondering, why not just increase the thickness of the asphalt layer so that it can withstand the weight of the truck, even with a mushy base? Then we wouldn't have to impose the spring load restrictions, and all our truck operators would be a lot happier. Well, that certainly is another possible solution to the problem.
And again, the engineers have the information we need. They've worked out just how thick a pavement layer needs to be to handle the estimated loads it will receive during its lifetime. By the way, in Minnesota, asphalt pavement is expected to last for 20 years. Even if a road was never used, it would most likely need rehabilitation in 20 years just because of oxidation from sunlight and the effects of rain, snow, freezing, and thawing. So the question is, how thick does the asphalt layer need to be? Well, here's one answer. If you have an asphalt layer already in place that has enough strength to carry vehicles with up to 9 tons per axle, and you want to raise the load carrying capacity of the road to 10 tons per axle, in most cases you'd need to add about 1.5 more inches of asphalt to the road. I can tell just by feel that it's stronger. The problem is that overlaying 1.5 inches of asphalt on a mile of road costs about $30,000 in 1991. If the decision to increase road handling capacity is based on the request of just one user who wants to carry a heavier load, we certainly might question whether the cost of the overlay is justified. On the other hand, if the road is going to receive a high volume of heavier traffic, then we might agree that it makes good sense to spend the extra money. But on yet another hand, let's see, I guess I need another hand here. It would have been cheaper if we could have forecasted increasing traffic volumes and load requirements and constructed the road with extra strength in the first place. Coming back later for any kind of upgrade is always less efficient than doing the job once. And we would have been able to allow bigger payloads from the beginning, so we'd get a higher return on our investment. Now, I've only given one hypothetical example. In a real-life question like this, it's important for an engineer to actually test the existing pavement to determine its true strength. Depending on the conditions at a particular site, more than 1.5 inches of overlay might be needed to reach the desired strength, or the pavement might already have the necessary strength so that nothing would need to be done.
Well, I think you can see that there are several factors to consider in deciding how to maintain our roads. But I hope I've been able to show that fair and supportable decisions can be made. In making those decisions, it's important to keep 3 things in mind. First, we need to plan ahead for traffic. How much can we expect on a given road, and how heavy will the loads be? Second, we need to factor in the weather, and that means actual local conditions which vary considerably across Minnesota. And last, we need to keep in mind that our city and county engineers can provide reliable, useful information to help make the decisions. Here in Minnesota, we can be proud of our national reputation for excellent roads, but the fact is we could do a better job of protecting our investment in pavement. With some good solid information
and a commitment to enforcing load limits, we can reduce our costs and serve the public better at the same time. That's such a good bargain for the people of Minnesota that we really can't afford to pass it up.